high TC semiconductor. This is in fact the technique was invented for this kind of thing to make high TC superconductor film. The other one, which is equally important, molecular beam epitaxy. Molecular beam epitaxy is often associated with gallium arsenide research in the 70s and 80s. And what you do is that you create two molecular beam or gas source, in this case gallium source or arsenic gas source, and these two combine on the surface, right? They induce on the surface, and then they create a lattice like this, gallium arsenide lattice. So this is one of the a traditional way of making gallium arsenide, that you have two molecular beams. This is why it's a bit of a misnomer. Really, nowadays people, when they do MBE, they don't really have a molecular beam. Molecular beam is a order trajectory of your atomic beam that come out. Really, what it reduce to is that the MBE is something that you introduce a gas in such a way that you will form a crystal structure in a very slow deposition way to build up this crystal structure slowly. So the deposition rate here is extremely small, so that it allows time for this gas to be in the right place. And so if you have monolayer deposition, right, one layer at a time, you are talking about MBE. The other thing, which is also very popular that you see in our department as well, is chemical vapor deposition. Well, the engineer does it too, especially in the electrical engineering department. You see all these big tube ovens. So let me give you an example of, you have all this glass tube oven, and you have wafer inside, and you pass gas through, okay, and you heat up this oven, okay, and what you're doing there is CVD, chemical vapor deposition. So you usually pass a molecular gas over, right, in different from molecular beam epitaxy. So this is why the name is a little bit misnomer, because you don't really pass a molecular beam. The beam is not molecule. The beam in MBE is actually atomic beam, right, atoms. Whereas in CVD, the beam that the gas you pass through is usually molecule. You have a precursor molecule. So for example, you have nickel chloride, right? So the idea is that you pass this chemical, which is a molecule, through this tube, usually a closed tube oven, and with this gas, and you're hoping that the gas will absorb on your substrate, and then you heat it up, and this precursor will then break it down, and it will give you nickel solid, for example, and the chlorine gas can come away. Okay, so you have a precursor. So in CVD, you have a chemical precursor, and then you heat it up, and then you flow through. Now, this technique is extremely popular in carbon nanotube research. And carbon nanotube research, you have a precursor, which could be a methane gas, right? And you have and you do it in the same way. Essentially, you do it in the same way. Now, the only difference is in carbon nanotube research, they use a small catalyst. They found if you deposit a little catalyst, maybe iron or nickel or something like that, nanoparticle on your surface, and the nickel acts as a catalyst, and then you have carbon nanotube grow in that way. And so in Shirley Tang's lab, they would have oven, CVD oven like this, and they would have catalyst, and they pass methane gas or some sort of organic chemical through, and they just promote the growth that way. Okay. So all of these, so it's very nano. All these things. So this is very electronic oriented gallium arsenide. This is very nano because in the surge the last 10 years, CVD technique have been used to make all sort of nanomaterial in the gas phase with a controlled temperature. So you will see people with a tube oven in their lab, and they have a bunch of control flow meter to control this kind of gas coming through. So it's extremely nano or technique that people use. The last type of reaction that I like to talk about is catalysis, and this has been used in a big way by chemists, especially in the petroleum industry, and more recently in green energy research, right? Fuel cell and so forth. And catalysis reactions are intertwined in the chemists, because the chemists design catalysis. So when you go to chemical engineering, they would have almost pilot plant style catalysts, and they've been working for this for years. And people in chemical engineering have been doing NINO for at least 30 years. They don't call it NINO, but they call it catalysis research. And what happened here is that the surface itself provides the site to promote the reaction, to increase the reaction. And there's numerous types of reaction that you could have. You could have exchange reaction, recombinated desorption, that's something that we talk about. Unimolecular, where you start on one reactant and then go into other product, single reactant. That's why you call unimolecular. Or bimolecular, whereby you have two molecules and they combine and give you reactants. And your catalyst, the purpose of catalyst, remember what is a catalyst? The catalyst does not get consumed in the reaction. All the catalysis does is provide an alternative reactive pathway, and this alternative reactive pathway has a lower activation energy, right? So because you have a lower activation energy, because of the Arrhenius equation, right? We say that once you get a lower activation energy, the reaction rate will go up. That's why catalyst is used, but it's not being consumed. So those three type industrial sort of oriented type reaction, and hopefully a brief tour will bring you in the right direction. Now, what about the reaction itself? How do you picture this, right? So we picture that there are a few steps, and I describe these steps, 7 steps, right, in a very generic fashion. Usually there's absorption of the reactant from the gas phase into some sort of Feser absorption state. We are thinking of absorption, so remember our absorption curve. First of all, below 5 kcal per mole, you have van der Waals interaction, so Feser absorption right here. As you continue to go on, you go into the chemical absorption state. It's more than 5 kcal per mole. Okay, so first you have Feser absorption. Then you may become chemical absorption, right? That's to become chemical absorption, and then you have surface migration of this reactant to the popular site or the favorable site, reaction site, and then the reaction, okay, occur, and then the finished up process. This product may then diffuse away from this reaction site, and then it go from this desorption site into chemical absorption state, right? This chemical absorption state into Feser absorption state, and then finally the product will leave and go back into the gas phase. Okay? And the key point is that what happened here? Okay, so we've been studying about absorption and desorption just now, right? What happened in this reaction step? And sometime in the whole this generic sequence that is required, not all the steps are involved. Some may go directly into chemical absorption state. Some may not need to move around, right? If the site is already enough, if that site is already the reaction site, you don't need to migrate and so forth. So these are just a general description, not necessarily all the steps are involved. And of course, when you talk about these steps, each of the steps will have its own kinetics.